Electrolysis.
We're now going to look at a very important industrial process, electrolysis. There are three different types of electrolysis: electrolysis of molten salts, aqueous solutions, and a process called electroplating. So we're going to define these three different types and also do calculations with them. At the end of the presentation, we will then conduct some stoichiometric electrolysis type of calculations as well. What is electrolysis? Electrolysis is the application of electric current to split a compound into its elements. And as a matter of fact, it is a way in which we have discovered many of the elements. The ending of electrolysis comes from Greek, which means to loosen up or to split up. Now, practically speaking, however, what an electrolytic cell is a cell that uses energy to cause a non-spontaneous reaction to occur. So, for example, if we have this reaction with this cell voltage, this is a spontaneous reaction. It's one that would proceed to the right and would generate 1.101 volts. However, if I wanted to run it backwards, as you can see, I would have to apply the same amount of voltage in order for the reaction to occur as written. And so an electrolytic cell, therefore, ultimately is really a voltaic cell, a galvanic cell, an electrolytic cell that is being run backwards. Many chemicals are produced by electrolysis. As a matter of fact, it is employed to manufacture and purify many elements and some compounds. For example, the aqueous electrolysis of water is used to produce hydrogen, chlorine, and sodium hydroxide, which all have important industrial uses. And so, therefore, electrolysis is a very important process in industry. There are three types of electrolytic cells. Cells that work with molten salts, cells in which we use aqueous solutions, and electroplating. Electroplating, typically you're applying a coating of a more valuable metal, like say silver or gold, to a metal of lesser value. And you probably are familiar already with electroplating. Electrolytic cells also are used primarily to produce desirable chemicals at a more, let's say, more economic cost, lower cost. Also to electroplate metals, or also to recharge a battery. Those are the typical uses of electrolytic cells. Let's look at the electrolysis of a molten salt, sodium chloride. Well, we take sodium chloride and introduce it in the cell, melt it, and then essentially the process is simply an application of direct current to the inert electrodes to obtain the products that are desired. The inert electrodes could be graphite, platinum, stainless steel, or some other suitable metal. So let's now look at the right side of this graphic first, in which we have a cell that we could construct in a lab. Of course, on the left, as you probably can surmise, we have here actually a cell that you would find in an industrial application. Okay, so let's look at the cell on the right. Here, just like in a galvanic cell, you have an anode. And at the anode is still where oxidation is taking place. And as you can see here, chloride ions are being converted to chlorine gas. However, even though at the anode oxidation is taking place, the source of electrons for the cathode is not the anode, it is the battery. We attach the cathode to the negative side of the battery, and as a result of that, the cathode sign, the convention that we use, the sign of the cathode in an electrolytic cell is negative, whereas for an anode the sign convention is positive. This is the opposite sign convention that you would find in a galvanic cell. Now, at the cathode, just like, however, as if it were a galvanic cell, okay, reduction is taking place. In this case, sodium ion is being reduced to sodium metal. Now, briefly, let's look at the commercial piece of equipment. Here we have a carbon anode. Of course, everything is immersed in molten salt. And as you can see here, as the chlorine is being produced, is channeled upward to some collection container. We also have, in this case, two iron cathodes at which molten sodium is being produced and channeled to another collection point. Okay, let's put some numbers on this electrolysis process. And this is the reaction. Remember, the cathode is our negative electrode now, and reduction is taking place there. And of course, we obtain this value from the potentials table. Anode is the positive electrode, and oxidation is taking place there, and we obtain this value as well from the potentials table. Now, if we add these two values up, we come up with a negative 4.07 volts. This means that to drive this reaction, we must have at least a potential of 4.07 volts. Let's now look at an electrolytic cell of molten aluminum chloride, and let's describe it fully. By the way, these items are all of the items you will be asked to use in order to describe the cell. First, you would need to draw a diagram of the cell. Then, for both the cathode and anode, you would have to list all the species that might be involved in a reaction and give the have cell voltage values. Next, you would have to use those values to calculate the voltage necessary to make the reaction run. Next, you need to write a balanced equation for the cell reaction. And lastly, you would have to probably describe what one might see visually at the cathode and at the anode. So let's describe let's start with A. Draw the diagram of the cell. Okay, here it is. For an aluminum chloride molten salt cell, I would have in the molten mass, all I would have is the aluminum ion and the chloride ion that are moving around. I would have also two electrodes, one the anode and one the cathode. I would have to describe indicate that the electrodes are platinum, as I've done here, by indicating PT. I have to indicate the sign of the anode and cathode, and I would have to show, of course, the cathode is attached to the negative side of the battery and the anode is attached to the positive side of the battery. Okay, next. Need to list all the possible reactions that would occur at the cathode. There's only one possible one. Aluminum ion going to aluminum, this would be the reduction of the aluminum ion. At the anode, all I could have occurring is the oxidation of the chloride ion. And now I will calculate the voltage necessary to make the reaction occur simply by adding those two voltages, have reaction voltages, and I come up with a negative 3.064 volts for the voltage necessary to make the reaction run. Then next, I write a balanced equation, and I would have to take it, of course, into account the electrons, and which means I would have to multiply the top the aluminum ion reduction by 2 and the chloride ion oxidation by 3, and come up with this overall balanced reaction. And finally, I would have to describe what I would see at the cathode. And what would I visually see? Well, at the cathode, I would see a silvery dull metal coating of aluminum building up on top of the cathode, and at the anode, I would see this greenish yellow and very noxious chlorine gas bubbles being produced. Let's now look at the electrolysis of water and water solutions. Well, whenever I apply direct current to water, this will occur. We will have essentially the splitting of water into its elements, which are our oxygen and hydrogen. The oxidation of water, of course, occurs at the anode, and it requires and the half cell voltage is negative 1.229 volts. The reduction occurs at the cathode, and that value is negative 0.830 volts. And by the way, this would be a good time to go to the table of cell potentials, both the one that you will get on the exam, in other words, the AP reference table, as well as the one that I've produced for you, where I include many more reactions and also much more clear about what goes on with water, both at the cathode and anode. Unfortunately, you won't be able to use mine during the AP exam, so you'll have to be cognizant of what goes on with the electrolysis of water directly from using the AP reference table. Let's look now at aqueous electrolysis. As you may have surmised from the previous slide, the fact that water can be reduced and oxidized as well could cause some competition with the reduction and oxidation of some of the ions in solution. Well, here are some examples. At the anode, if I am trying to oxidize the bromide ion, of course now from the table I get that the oxidation of the bromide ion requires 1.06 volts, and I am to compare that with the oxidation of water, which requires a higher voltage. One can safely say that the bromide ion, therefore, will oxidize first until it's all been completely used up, because it requires a lower voltage. However, in competition with the fluoride ion, water will oxidize first. Why? Because the fluoride ion requires a much higher voltage than water does. At the cathode, on the other hand, if I compare the reduction of iron 2 to the reduction of water, once again I see that the reduction of iron 2 will occur first because of its lower potential, but if I were in competition with lithium ion, water will be reduced first, simply because the lithium ion requires a much higher voltage. And by the way, if we were ever to produce lithium in the presence of water, what do you think would happen? Think about it for a moment. It's an alkali metal. All alkali metal react violently with water. So even if we were to produce lithium, it would immediately react with water and go back to being an ion. So in general, for aqueous electrolysis, the rule is this: any reducible substance must require a lower voltage than that of water in order to be preferentially produced. Any oxidizable substance, conversely, must also require a lower voltage than that of water in order to be preferentially produced. Or more simply put, Oxidation and reduction reactions with potentials closer to zero are the ones that generally occur. However, please keep in mind that the half cell values are are just typically, just guidelines. There are other concerns such as kinetics that could change the picture somewhat. But let's see what you have learned. Can you reduce the manganese to ions in water to manganese? Can you oxidize copper to copper 2 in water? Come back when you have an answer after pausing the presentation. Well, here is the information that I would get from the potentials table. Since water is reduced with only a potential of negative 0.830, I cannot reduce the manganese 2 in water. What about copper being oxidized to copper 2? Well, water oxidizes at a higher voltage value, therefore yes, this is possible. Okay, let's now look at the aqueous electrolysis of sodium chloride, putting some numbers on it, and see what kind of products we get. Well, as you will see in a moment, the aqueous electrolysis of sodium chloride certainly does not give the same products as that of molten sodium chloride. At the cathode, we could have two possible reactions. We could have the reduction of the sodium ion or the reduction of water. Which one do you think will take place? Well, obvious, right? The product that is formed in the cathode in this case is hydrogen because it requires less energy in order to be produced. Now, compare that to the electrolysis of molten sodium chloride. What got produced there? Well, sodium got produced there because there was no competition with water. That's the difference. At the anode, I could have the production of chlorine or the production of oxygen. Now, one would think by looking at these values that water will get oxidized before chlorine will. However, in part because the the values of the energy required are about the same, and also because there's another factor called kinetics. Essentially, in practice, only chlorine gets produced, or just about all chlorine gets produced. Why? Because the rate of oxygen production is lower. It's kinetically controlled rather than thermodynamically controlled. And this factor brings up to another point, which I'll treat in the coming slide. That concept, actually, that practice, which is called overvoltage, is the excess voltage that is required to be applied to the cell, to the electrolysis cell, in order to appreciably produce the desired product. So, as you well know, the reaction with the least negative value for the half reaction potential is the reaction that is most likely to occur. However, in many half reactions, particularly those involving gases, because of kinetic control at the electrode surfaces, a higher voltage than calculated is required in order for the reaction to proceed. Well, let's see what you have learned. Let's see if you can figure out the electrolysis of sodium fluoride. Here's a hint. The solution becomes very basic at the cathode and acidic at the anode as the reaction progresses. So, what reactions are occurring at both electrodes? So here are the answers. Well, at the cathode, the sodium ion could be reduced to sodium, or water could be reduced to hydrogen. Well, which one do you think will occur? Well, water definitely is going to be reduced to hydrogen, and that'll make the solution more basic. That was the clue. At the anode, the fluoride ion could be oxidized to fluorine, or water could be oxidized. Obviously, oxygen is produced, meaning water is going to be oxidized, and that will make the solution more acidic. Here again is the other clue. Now, let's add up both reactions that are occurring at the anode and cathode and see what overall reaction we get and what the cell voltage would be. In other words, the voltage required to run this reaction. That voltage is a negative 2.06 volts. The overall reaction is, as you see, or just more simply put, it is the decomposition of water. See if you can do this problem on your own. Come back when you're done. Okay, welcome back. Here's a diagram of the cell. And here are the answers. Well, for the cathode, we have copper 2 possibly reduced or water reduced. In this case, which one do you think will be reduced? Well, copper 2 is going to be reduced simply because it's spontaneous. It's a positive value. Doesn't require any energy for it to occur. At the anode, we have these reactions possible. Which one do you think will be oxidized? Well, the bromide ion, since it requires less energy. Well, here are a couple of questions you may have been asking yourself. How do we know what competes with what? Why not compare copper to water, oxidation, Hef reactions? Well, of copper, it's copper 2 that is present in solution. That could only be reduced. So it must be compared with the reduction of water. And in the case of bromide ion, it cannot be reduced any further, so it can only be oxidized. Therefore, it must be compared to the oxidation of water. So let's end the calculations by calculating the voltage necessary to make the reaction occur and writing a balanced equation. So the reaction in the copper 2 bromide cell is simply this. We add the two Hef reactions into our complete reaction, and we get a voltage. We get that this reaction requires, in order to run, a negative voltage of 0.73. By the way, on an AP exam, you may be asked to describe visually what occurs at the anode and cathode. And here are some typical solutions or products and their colors and appearance. Just take a look at this slide and do your best to remember as many as you can. Let's talk now about electroplating. It is the process of coating one metal onto another. Usually, the object that is being coated, electroplated, is cast of an inexpensive metal. And the coating is a thin layer. By the way, the coating that we apply through electrolysis is a thin layer of a metal that is either more attractive, corrosion resistant, or more expensive, such as in the last case, such as silver or gold. We also use electroplating to purify metals. Okay, so electroplating has one important difference from the previous two electrolysis cells we have talked about, because electroplating uses active electrodes. The previous two used inert electrodes. Now, the plating baths could be either aqueous or molten. Kind of depends on whether the water redox reactions interfere with the desired product, or also, there's some special desired appearance we might want to provide to the plated article, and therefore those two factors determine the choice as to whether the plating bath will be aqueous or molten. Now, when we electroplate in aqueous solutions, however, what happens is simply this. The anode electrode dissolves, meaning it's oxidized, and replaces an ion in solutions, which then plate onto the cathode. So this is actually a very important application for purifying metals, because I could start with a crude, impure copper 2 anode and a very small pure copper cathode, and I place everything in a copper 2 solution. Then as the anode dissolves, the impurities that are in solution remain in once the crude copper dissolves in solution and becomes copper 2 ions, the impurities that are not copper 2 ion remain in solution and typically sink to the bottom. And the copper 2 ions that have been obtained from the anode now plate onto the cathode and can provide a cathode, a bar of copper that is very, very pure. It can be as pure as 99.95%. Alright, so let's now go through the electrolysis of aqueous sodium bromide using silver cathode and copper anode electrodes. By the way, how would one know that this is an electroplating situation? Think about it for a moment. Well, you should realize immediately this is potentially an electroplating situation because the electrodes are not inert. They're not stainless steel, they're not graphite, okay, or platinum. So let's go through this example. First of all, let's draw the diagram of the cell. And here it is. This is drawn, sort of like exactly like the other cells is. Let's now look and see what happens at each electrode. At the cathode, I do list silver, the cathode itself, as a potential reaction, but in this case, obviously, silver cannot be reduced, and therefore silver is not going to react in any way. However, I could have the reduction of water, I could have the reduction of the sodium ion, and obviously at this point you would expect water to be reduced. At the anode, I could have the copper electrode itself be oxidized. I could have the copper electrode also go to the copper 1 ion instead of copper 2. I could have the oxidation of water. I could have the oxidation of the bromide ion because that's what is in solution. So it seems like the most likely reaction to occur here is going to be the oxidation of copper to copper 2 because it has the lowest voltage requirement. Okay, now we actually have to revisit what happens to the cathode. Why? Well, let's list all the reactions that we listed before, but here's something else that could happen, because see, we now have put copper 2 into solution, and copper 2 could reduce to copper. And guess what? Because copper has a positive voltage, meaning it's spontaneous, it will immediately reduce. Therefore, I not possible to really show an overall reaction because it wouldn't make any sense. However, the plating reaction that is occurring is simply the reduction of copper 2. This is the reaction of the cell. So, what would you see at the cathode, at the anode? Well, the cathode, there will be a building up of the copper metal. At the anode, there will be a mass loss. The solution, and of course you would have a very blue solution of copper 2 right around the anode. Let's now talk about the last topic, the stoichiometry involving electrolysis. If I want to determine the mass of an element deposited at an electrode, the sequence of calculations is simply this: current times time times the fact that 1 mole of electron is equivalent to 1 Faraday. And for 1 mole of the element, I could have several moles of electrons. And once I have moles of the element, I can certainly convert the moles of elements to mass using the molar mass relationship. In this case, the current is in amperes, but more specifically, it's in coulombs per second. The electrical charge, which is in coulombs, equivalent to current times time. And again, as I said already, the electrical charge for 1 mole of electrons is equal to 1 Faraday. Same thing as saying 96,500 coulombs. So in terms of units, here is how the dimensional analysis series of calculation works out. Current coulombs per second, and as you can see, I am able to get rid of the coulombs. I can get rid of seconds. Then of course the 1 mole of the element per 1 Faraday is equal to 1 mole of the element per 96,500 coulombs. And then next thing I do, I convert all of this to moles of the element using the relationship that exists between essentially the mole of the element and the moles of electron, meaning the charge of the ion. Okay? Because what I'm trying to say is this: if I have copper 2, okay, and I'm trying to figure out how many, what the mass of the copper 2 that's being deposited on the cathode is, well, I know to reduce copper 2, I have to provide it with 2 moles of electron for every mole of the element. Well, it's the same as the charge of copper 2. Okay, and then once I have moles of the element, well, that's easy. I can easily convert it to grams of the element. So here is how the units work out. Of course, if you ask to figure out the current required, you're going to have to rework this dimensional analysis to give you what you want. Let's see if you can come up with an answer for this problem. Pause the presentation, come back when you have an answer. Okay, well, this is the reduction reaction that would occur at the cathode in this case. So if I now plug in all the information that the problem gives me, starting with the 2.00 amps of electric current, which is the same as saying 2.00 coulombs per second, times 20 minutes, which I convert to seconds by multiplying it by 60 seconds per minute, times 1 mole of electrons per 1 Faraday, times 1 mole of copper metal per 2 moles of electrons that are needed in order to reduce the copper ion, times 63.55 grams of copper per 1 mole of copper. Now, canceling out all the units as needed, I am left with grams. which is what I need. I do the calculation and I get that the grams of copper deposited at the cathode are 0.790 grams. How many minutes will it take to deposit 0.50 grams of nickel from a nickel nitrate solution on a metal object using a 3.00 amp current? Now, for this problem, you're going to have to rework the calculation or the series of dimensional analysis calculations to get to the answer. See what you can come up with, and come back when you have an answer, a solution. All right. Well, here's again the reaction. Now I have reworked the series of the dimensional analysis series to give me the answer that I want in the units that I want. And if you work this calculation out, you will get 548 seconds, or same as 9.13 minutes. We have come to the end of the presentation. Please contact me if you have any questions.